Hi, my name is Jiayang, and I will walk you through our project, which is generating photorealistic super-resolution images with generative adversarial network. So now let's first give an introduction. Super-resolution has been one of the most well-researched topics in the field of computer vision for some years. Among all of those modern approaches, we will mainly talk about SR-GAN, which is the state-of-the-art super-resolution model proposed in 2017. It is the very first super-resolution model that achieved photorealistic super-resolution on 4x upscaling images. Yet, if we take a closer look at its generated images, we can see that the perceptual difference between generated images and high-resolution images are still very large. Now, let's talk a bit more about SR-GAN. As I mentioned earlier, SR-GAN is a generative adversarial network aiming to perform single-image super-resolution in a typical GAN setting to solve the min-max problem. The generator performs the super-resolution on the input images, while the discriminator attempts to distinguish between the ground truth high-resolution image and the high-resolution image generated by the generator. Unlike a normal GAN, where the generators are not very deep, SR-GAN utilizes residual blocks from ResNet and is able to reach a fair depth for this task. The discriminator, on the other hand, resembles what is normally seen in other GAN models. One of the aspects that distinguishes SR-GAN from other models, besides the use of residual blocks in the generator, is the unique loss function it proposed. SR-GAN introduced a new set of losses called perceptual loss and is formulated as a weighted sum of content loss and adversarial loss. As the original SR-GAN was trained on 4x upscaled images, we trained an implementation of the original SR-GAN on 8x upscaled images to see how it performs when the task is more difficult. To our surprise, we see a drastic drop in PSNR/SSIM metrics, as well as diminished generated image quality. Now, let's talk about our takes on super resolution. So the first modification we make to SR-GAN is we introduced an additional loss called total variation loss that derives from total variation denoising in signal processing. In general, total variation loss will compute the sum of the absolute differences for neighboring pixel values in the input images. Minimizing total variation loss would mean minimize the occurrence of repetitive, boxy artifacts since they inherently have high variation loss. As you can see in the image generated on the right, not only is the TV loss able to fix the color distortion, it also ensures a clear image without too much artifacts. As we explore deeper into SR-GAN structure, we realize that the residual blocks in its generator may not be the best idea. Instead of using residual block, we used residual dense blocks, where each block contains only convolution layers and leaky value units. At the same time, each block is connected to all the successor in one RRDB module. Traditional adversarial loss functions focuses on whether or not a given image is fake or real. We use a relativistic adversarial loss that focuses more on whether a real image is more realistic than the generated fake image. As this loss contains both real images and fake images, the generator benefits from gradients coming from both of these images. Although the metrics are not as high as just applying the TV loss, we can still see that the generated image here contains more high-frequency details. In order to have the generator generate high-frequency details, we think that it would be a good idea to let the discriminator guide the generator. We apply discrete wavelet transform to reconstruct the image into 4 channels. 3 of such channels represents the high-frequency features of the original image, including horizontal details, vertical details, and diagonal details, respectively. HF discriminator is trained to distinguish the high-frequency feature of high-resolution images from the high-frequency features of the super-resolution images. Thus, by being able to distinguish high-frequency details, this discriminator will favor generated images that contains more high-frequency details. This appears to be our best model so far. Not only does it contain more detail, it also manages to remove the redundant transparent boundary around the object presented in RRDB models. So in general, in this project, we explore the modification choices on original SR-GAN to improve its performance on the 8x upscaled images. We observe that current images generated using SR-GAN are lacking certain details and can be improved. We introduce additional loss to smooth the artifacts presented in SR-GAN generated images We introduce residual and residual dense block to replace the residual block in the generator to facilitate training and prevent instability. We also introduce relativistic discriminator and high-frequency discriminator to guide the generator to produce images that are detail-oriented. As such, it concludes our presentation. Thank you very much for watching.